determine the reactions of the supports. Okay, here we have a 6 meter span simply supported beam. So on the right hand side we have a simple support and or a pin support, and on the left hand side we have a roller support. So this support is roller support, and this particular support is called simple pin. Support. So in the roller support, the displacement of the beam is permitted in the horizontal direction, but it's restricted to move upwards. And whereas on the simple support, only rotation of the beam about the pin or about this point B is allowed. Other movement towards any point is restricted. Okay. So what we need to do is to draw is to first draw a free body diagram for this beam. So we have a 6 meter span beam. So on the roller support, we're going to be having this vertical reaction AY. Well, let's call it NA. It's customary to call this single reaction N. So normal reaction at point A, single. We have a single reaction force. And at the pin, we have BY and BX. Okay, and here we have a trapezoidal load starting from 900 Newton meter and going down to 600 Newton per meter, and then like that. We have this trapezoidally distributed load, and then we have this uniformly distributed load with a magnitude of 600 Newton per meter, and we have this magnitude here 900 Newton per meter. Okay, so essentially what we are going to do now is to write equilibrium equations. So equations of equilibrium. Okay, so one thing that we need to do here is to reduce these distributed loads into equivalent single loads. Okay, so what we need to do, okay, so let's draw the beam again. Right, so we have NA here, we have BY here, we have BX here, BX, BY, and NA. So what we need to do is to, okay, so this is our trapezoidal distributed load here, and we have this uniform distributed load here, right? So the equivalent 1.5, I'm sorry, we have 3 meter here, so acting right at the middle here, the equivalent single load will be equal to the area of this rectangle, and that is 600 Newton per meters times 3 meters. Okay, and on the other hand, okay, sorry, let's do the following. Let's delete all these and let's focus on one single triangle, one single uniform distributed load that I'm feeling now, hatching. Okay, so the equivalent single force representing the action of this whole 6 meter, the 6 meter long and 600 meter per meter depth rectangle. So that would be passing through right in the middle, and that would be equal to 600 Newton meter. This area that I hatched, 6 meter. Okay, so that would be triangle. Or that would be the magnitude of the equivalent force. And on the other hand, we have this triangle here, okay, that I'm hatching right now, and this would be passing through 1, 2, okay, so 1 meter, 1 meter, and 1 meter. So the centroid of this triangle passes through this 1 meter here. So the equivalent force would be acting like that, and the magnitude would be equal to, so this one would be 300, because this is 600, and this is whole depth is 900. So the magnitude would be the area of this triangle, and that's 1/2 times 300 times 3. Okay, so we end up with this this equivalent force, and support reactions. So based on that, we're going to be writing the equilibrium equations, which is the sum of the forces in the area. Okay, like we can straight ahead go and write moment equilibriums. Let's see. Okay, so if we write some of the moments around point B here, it's really easy to find NA. So let's do that. So it's up to us. Okay, so the strategy is up to us. Okay, so based on that, I am now writing moment equilibrium equation and taking moments around point B, and anti-clockwise it would be negative. So I'm having like a negative NA, so negative NA times 6 meters, okay, and I will be having plus, so this is 600 times 6, 600 times 6, and the distance is from here to here, 3 meters, okay, that would be that, and plus the second equivalent force 1/2 times 300 times 3, and the distance would be 3 plus 1 plus 1, 5. Okay, so that would be 5 meter. So that's 0, and from here we're going to be finding NA equals 2,175 newtons, and that is equal to 2.175 kilonewtons. Okay, so that's that. And for By, we can write moment equation around point A, and that would be equal to 0, sum of the moments. So By times 6, anti-clockwise positive, minus 1/2 times 300 times 3 times 1 meter. Okay, so that's the moment arm, and minus 600 times 6, and the moment arm for this is 3 meters. Okay, so that's 0. Okay, from here, By will be 1,875 Newton, and that is equal to 1.875 kilonewton. Right. And as for Bx, it's very straightforward. Yeah, it's very easy to see that in the x direction there is no applied force on the beam, so the reaction would be 0. And for that we can write sum of the force in the x direction should sum up to 0. So we have like Bx equals 0. Bx will be equal to 0. Okay. So Na is 2.175 kilonewton, By 1.875 kilonewton, and Bx is 0. Thank you for listening.